Okay, so there are a few things that I'd like to do today. And the first is maybe just to go around and I'd like to remind myself of who's a graduating senior, and then to ask among the graduating seniors, what are your plans for after Kent State? I'm just curious about that. And so I can turn off the recording for that, on for them. All right, recording is back on for the other stuff coming up. All right, so today's the last class, and I am quite willing to do an extra question and answer session with you guys on tomorrow or Wednesday, if you wish, or not if you don't wish. That's really totally up to you. If anybody wants that, you can speak up now or type in the chat or whatever you like. If we do a question and answer session, I'm not going to prepare anything for that, okay? And so I will just answer questions. And if you don't have questions, then I will just wish you good luck and goodbye. Does anybody want to schedule something like that for the next couple of days? Perhaps not. I'm not seeing a lot of people jumping for that. Okay, never mind. Then this will just be the last class, and then we can move on to the final exam on Thursday. So the final exam, we talked about the format of that before, so it's going to be similar in style to the midterm, but a little bit longer than the midterm because it's a final. It will be similar also to the practice exams that I posted on the Google Drive, so you can take a look at those things. This is, not meant to be a killer exam. Right? This is meant to be a plain vanilla exam for this type of quantum mechanics. And so, sometimes I misjudge in one direction or the other. So if it's too easy or too difficult, I apologize, but it's meant to be, a standard kind of exam for this level of course. It is certainly not meant to take you 24 hours, right? It's meant to be the sort of thing that you could do in 2 or 3 hours. And so you have 24 because that way you can have extra time. And also, I know some people have other commitments. And so this way you should be able to find 2 or 3 hours to work on it during the range of time. So that's going to begin on Thursday at noon and end on Friday at noon. And so please do email me your papers by Friday at noon. All right. Any questions about the exam or practical things associated with that? No. Okay. That is all fine. So you have a homework that's due today. Please send it to me at some point today, and then I will turn around and grade it and get it back to you in case you want to check your answers before you prepare for the final. I understand that Kent State will have sent you some kind of student questionnaire by now to evaluate the course. And so please do fill out that and send it back if you have not done so already. And, just for the benefit of future students. And yeah, so hopefully it'll be helpful for somebody. Okay, so for the rest of this class, I wanted to just go over the things from the semester just as a kind of review, because we've covered a bunch of stuff. And so let me sort of go over the list of things just to refresh your memory. Okay, so I'm going to connect my iPad again. And as I mentioned a little while ago, I have a new method for connecting the iPad. And so let's see if this works without causing a lot of extra noise and without causing any other unforeseen problems that I know about. Okay, let's see. So do you see an iPad screen now? Yes, somebody. Okay. You see the whiteboard. Excellent. Okay. So let's see if this all works and doesn't cause any horrible disasters. Okay. So to review the things that we've gone through in the semester. So the idea in chapter 1 was just to learn about the idea of a wave function. So the psi of x and t. Okay. Just to make sure, you can see that I'm writing things on the iPad screen, right? Okay, good. This is really a key concept in quantum mechanics, right? The concept that matter is described by a wave function. And that's not obvious, because normally we think of particles with a specific position and velocity or momentum, right? But the idea in quantum mechanics is that particles have wave-like properties. And so you need a wave function to describe them. And then if there is a wave function, it has to evolve in time through some kind of partial differential equation. And so the partial differential equation has to tell you how the wave function changes at every x, okay? And so in this case, it follows Schrodinger's equation. Okay, and so this is something which is first order in time. And second order in position. All right, and then a lot of the first chapter had to do with seeing how information is encoded in the wave function, so that if we could solve for the wave function, we would know what to do with it. And so this gave us the statistical interpretation of quantum mechanics, or a statistical interpretation of the wave function, right, which says that the magnitude of psi, the absolute magnitude squared, times dx is the probability that a particle is between x and x plus dx. Okay, so that's the way you have to talk about probability when you have continuous variables. Right, is that you have to include the dx factor to make a kind of tolerance of saying, how precisely do we care about the particle being at a certain position? Okay, and so based on that, we talked about probability calculations. We talked about normalization. And the point there is that probabilities always have to add up to 1. And so there has to be a probability of 1 that the particle is someplace. And so if you integrate over all the possible positions, you have to get 1. And so that's been a step in all of our calculations throughout the semester. So I can give away things like that on the final too, right? That where you have to say what is the normalization constant so that the total probability will come out to 1. Okay, and then once we had the normalization, we could talk about expectation values. Or in other words, averages. Okay, and so we have the expectation value of X, or the expectation value of X squared, right? And then based on looking at how the average X evolves in time, we found the momentum operator. That's this P hat, which is minus I H bar d by dx. And then we got the expectation value of P and the expectation value of P squared. Right? And then based on those things, we could define the uncertainties. And this led us to the uncertainty principle, that the uncertainty in X times the uncertainty in P has to be greater than or equal to H bar over 2. And we had a bunch of examples of that, where there will be a specific wave function, and you can calculate both of the uncertainties and check out that they both come out to be, that the product comes out to be greater than or equal to H bar over 2. Chris, is that a question? I can't hear you.
Oh yeah, sorry about that. Just so you know that the last line you wrote, we can't see. It gets cut off in the screen. Maybe it's just me.
That's interesting.
Can anybody else see it? No?
Anybody see the uncertainty principle that I wrote? That's interesting because
yeah, it's like half
can.
cut off.
some people see it, some people have it cut off. Maybe it depends on whether you're watching on a computer or an iPad or a phone, something like that. Okay, good to know. Thank you for telling me. Brian can see it on a computer. Yeah, and I see it on my computer screen. Okay, so I'll know not to write down way at the bottom. Okay, thank you. Yes, and all that I wrote is something, hopefully familiar to you. Do you see it on the top of the screen up here? Right, okay. Sigma X, sigma P greater than or equal to H bar over 2. Okay, good. Now, those were the highlights of chapter 1. Okay, so then chapter 2 moved on to solving Schrodinger's equation. For one-dimensional problems. Okay, so this is something that we did using separation of variables. So that's a method that might be familiar from math classes. It might be familiar from E&M classes. But if you haven't taken E&M, well, then you've learned it here, and you can apply it in your E&M, and then hopefully the E&M will be easier for you. Anyway, this technique led us then to the idea that the wave function in terms of X and time has a separable solution which is the time independent lowercase psi of x times e to the minus I energy time over h bar. Okay. So this is a separable solution. And then the general side would be a sum of a lot of separable solutions. So the general, here I'll say psi general of x and t would be a sum of many such separable solutions, each with its own time-dependent complex exponential factor. Okay, and then this is the general concept, okay, and we applied that concept to 4 sample problems. And those problems, you remember, were a particle in a 1D box, the harmonic oscillator, the free particle, and the delta function potential well. And Chris, you can still see where I was writing just there? Okay. Okay, and so for the first 2 things, we had a set of discrete states. That is, we could count the states, right? State number 1, state number 2, state number 3. Right? For the free particle, that's different. There we had just continuous set of states. And a related distinction is that the first 2 problems had only bound states. That is, states where the particle was bound close to the origin. That is, there's some limit on how far away from the origin it could go. All right? Whereas for the free particle, it is not bound. And the opposite of bound is a scattering state. All right? And then the delta function potential well is interesting because it has both discrete and continuous. That is to say, both bound and scattering states. Right, so those were some of the highlights of chapter 2. And then another highlight that we got out of that is the method for solving the harmonic oscillator. That is, the method involved all these tricks with operator algebra. The tricks with raising and lowering operators. And so, that's a method for solving the harmonic oscillator, but it's also a method that we used again later on when we were dealing with angular momentum. And for those of you who go on and take more advanced quantum mechanics courses, that's a method that's going to come up a lot. And it's really the key for some more advanced versions of quantum mechanics where the idea is a raising operator actually creates a particle somewhere, right? That is, you have a wave function for the universe, and there's a raising operator that adds an electron in a specific position in the universe. And there's a lowering operator that removes an electron from a particular position. And so that's an important theoretical concept that will come up in future courses if you take future quantum mechanics courses. All right, so that is a summary of some of the highlights of chapter 2. Okay, and then from there, we went on to chapter 3 about the mathematical formalism of quantum mechanics. Okay, and this is a more abstract subject, which some people like it, some people don't like it so much, but it's a general approach that gives us guidance for some more complicated problems, and especially for the spin-related problems that are coming later. Okay, and so here the idea is that we have a Hilbert space that is the space of all normalizable functions. And we know that's normalizable, not normalized. Okay, and so that distinction is important because it's only if we include all normalizable functions that this is really a vector space. Okay, and then, if we consider that as a vector space, then we can make a whole bunch of analogies between the differential equations that we do in quantum mechanics and linear algebra, right? So here are some of the analogies, right? That wave functions correspond to vectors. Operators correspond to matrices. The integrals, all of these integral sandwiches to calculate expectation values, those things correspond to inner products, like a dot product of vectors. So a product of vectors that gives us a scalar. And then observables, that is anything that we can observe, corresponds to eigenvalues of Hermitian operators. And determinate states, that is, states with a specific value of some observable, they correspond to the eigenvectors, again, of Hermitian operators. So this is a set of abstract comments which apply to general operations with wave functions. And then they also apply to situations where we really wouldn't otherwise know what to do, right? And so that's the situation for spin in particular, right? Because we don't have a real visualization of what it means for a point-like particle to spin. And so, we need to follow the rules for concepts like this. Okay, so I am looking at the chat just now. I see a message from Swastik that didn't show up, that I didn't notice before. Remove the mouse pointer at the taskbar to be able to see it. Swastik, are you talking about something I should do or something that the students viewing should do? That you should do, that Chris should do. Okay, did it work, Swastik's tip?
I ended up resizing the screen I was seeing. I think my computer was overscanning what you were sharing, so I just resized everything down. So I'm good now, though.
You're good now. Okay, great. Right. Well, I need to know how these things look for people. It's possible that this will be the last online class that I teach in my life. Maybe I'm going to be going back to teaching in person next fall. Maybe, or maybe not. Maybe I'll be teaching online for the rest of my career. We just don't know. And so it's good to be aware of how everything comes across. Thank you. Okay, what else did we do in chapter 3? We did a lot of things in chapter 3. We proved some stuff about the generalized statistical interpretation. And part of that was the generalized uncertainty principle. Okay, and let's see. We proved about the time derivative of an expectation value, right? That the time derivative of an expectation value of Q is related to the commutator of that Q with the Hamiltonian. So the Hamiltonian is really a special operator. It's not just any generic operator. It's a special operator that tells us how things change in time. And it has a special role in Schrodinger's equation. Okay. Oh, and then I guess the last thing I should mention in this summary was the Dirac notation with the bras and kets. So that's a nice compact notation for quantum mechanics. And it's a notation that guides us to thinking about inner products and all that kinds of stuff we have to do. All right, so now, once we are prepared with all of that theoretical toolbox, right, then we could go on to chapter 4. To chapter 4, which had to do with quantum mechanics in 3 dimensions. Okay, and so when we're working in 3 dimensions, right, one way that 3 dimensions is different from 1 dimension is that we have a choice of coordinate systems. Right? In 1 dimension, there's just one coordinate system. It's kind of simple, right? But in 3 dimensions, we have to choose. Are we going to work in Cartesian coordinates or spherical coordinates or something else? And there's other things that we haven't talked about in this course. Okay, but in this course, we did 3D Cartesian coordinates. And that was useful for a particle in a 3D rectangular box. Okay. And then we also did problems in spherical coordinates. And that's useful for problems that have spherical symmetry, which is more common, right? That's a more common thing. There aren't that many rectangular boxes in nature, but there are a lot of spheres in nature, okay? And so for the solution in spherical coordinates, well, we did the general separation of variables. Which led us to the class of functions called spherical harmonics. And you remember, of all the different special functions that we talked about this semester, the spherical harmonics are my favorites, right? And so these are the ones that I actually recommend learning about, unlike all the other things, which, you know, I can take them or leave them. Okay, and so then, you know, as a couple of specific examples of that, we had the particle in a sphere, or the hydrogen atom. And, you know, the hydrogen atom is really the very important case, right? I mean, it's the case that really makes the foundations of chemistry. And so this is, you know, what historically persuaded people 100 years ago that quantum mechanics was really important. And, you know, it continues to be, you know, probably the single most important solution that comes out of a course like this. Okay. But then we besides just solving the hydrogen atom, we also did more theoretical stuff in 3 dimensions. And so we talked a lot about orbital angular momentum. And so we figured out all the commutation relations associated with that. And so that leads to a kind of operator algebra that's, as I said a few minutes ago, it's kind of similar to what we had with the simple harmonic oscillator. And based on that, we could solve to find the eigenvalues and eigenvectors, or I could say the eigenfunctions associated with orbital angular momentum. And then we did related stuff with spin angular momentum. So the idea there was that, you know, in addition to orbiting, you know, to have angular momentum associated with the position of the particle, you can also have a particle that just spins in place, and or it could do both, right? But if it has spin, that's a different form of angular momentum, which has another spin quantum number. And this can be a half integer, unlike orbital angular momentum, which has to be an integer. Right? And the most common case for particles like electrons is spin 1/2. And then the states are represented by spin vectors, or spinors for short. And the spin operators are represented by Pauli matrices. And so we can use those things to calculate expectation values of the X or Y or Z components of the spin in any particular state. And briefly, I spoke about addition of angular momentum also. Okay, so that was chapter 4. And then there were a couple of other chapters that I just talked about more briefly towards the end of the semester. Okay, and so in chapter 5, that was concerned with identical particles, indistinguishable particles. And that led us to the distinction between bosons and fermions. And that's a distinction which is related to the spin of the particles, that bosons have integer spin and fermions have half integer spin. So a typical example would be that electrons are fermions. And so we talked about how to make wave functions that have the right symmetry for bosons or for fermions. Right? And so for bosons, we need to have a wave function that is symmetric under exchange. And for fermions, we need a wave function that's anti-symmetric under exchange. And anti-symmetric means that it changes sign under exchange, right? And even though you might initially think, who cares, right, about the sign of the wave function, actually it matters, right? And we tried to work out some examples, either through algebraic calculations or through Mathematica 3D plots, where you could see that the distinction between bosons and fermions really makes a difference, right? And that when you have this symmetry requirement, the particles can actually influence each other, even if there's no potential energy between them. And so bosons have an enhanced probability of being close together. Fermions have a reduced probability of being close together. So the distinction actually matters. And then the last thing that we talked about in the last week of the semester was in chapter 7 about perturbation theory. And so that has to do with a method for solving problems that are close to exactly solvable, even if they are not themselves exactly solvable. Okay, and so something like that would be, the particle in a box with a little bump at the bottom of the box. Right? And so a problem like that is close to exactly solvable. And so there's this systematic method to say, well, we have the solution for the original unperturbed, exactly solvable problem. And then there will be a little correction that has to do with what's the perturbation. And so there can be a first order correction and a second order correction. And the first order correction is actually not that complicated. The first order correction is that you take the perturbed Hamiltonian, that is the change in the Hamiltonian, away from the exactly solvable problem, away from the original problem. And you just stick it in an inner product with the state of the original problem. So you make this inner product with the wave function or the ket of the original problem. And the corresponding bra over here. And this inner product tells you the first order correction to the energy, En. So this expression for the first order correction is not that complicated. It's probably worth remembering. The second order one is harder than this. It's messier than that. But the first order one is actually not that bad. Okay, so that's kind of a summary, right? My half-hour summary of what happened, over the course of this semester. And so, some selection of these things will be on the final exam on Thursday and Friday. So to wrap up here, let me just say something about the goals of this study. Either for students who continue on in physics or for students who go into other fields. All right, so for those of you who are continuing on in physics for graduate school or for your careers, you will presumably be studying more advanced levels of quantum mechanics, right? And so you will be studying further levels, and hopefully this will be a preparation for that. But also, it's a preparation for any subject within physics where you have a function of position. You're dealing with fields, which are functions of position or functions of position in time, right? And so this happens with electric fields or magnetic fields, right? That there's an electric field vector, which is defined everywhere as a function of X, Y, Z in time, or the same for a magnetic field. Or in my own field, my own subject of liquid crystal science, we have molecules that are pointing in a particular direction. And so we speak about the director field for molecules to say that molecules over here tend to be pointing in this orientation. The molecules over here are pointing in some other orientation. So we have a vector to characterize the orientation of the molecules, which depends on position and time. And so then the theoretical concept of solving for a wave function that depends on position and time, it could be applied to solving for anything else that depends continuously on position and time. So it's a very broadly applicable idea in that sense. So that's for those of you who go on in physics for graduate school or careers. Now, some of you may take your physics education and go on in other subjects besides physics, and that's, of course, totally fine also. I guess, we have a couple of goals for how you can take, a physics bachelor's degree and apply it to other subjects that you might want to do in the future. I can speak about physics in general, or I can speak about quantum mechanics in particular, right? So for physics in general, the idea here is that it's a precise way of thinking, which is hopefully going to inspire you to similar precision in other kinds of things that you do. In particular, in physics, we try to be very aware of the relationship between our assumptions and our conclusions. And so to think about which assumptions lead to which conclusions, and if we change some assumptions, how does that change our conclusions? And that's worth applying to other parts of life. Another important point in physics is that we try to separate what is inherent in the world versus the arbitrary choices that we make in describing what's going on in the world. So one kind of arbitrary choice is the system of units that we use, right? Whether we use metric units or traditional British units or anything else, right? Another kind of arbitrary choice has to do with coordinate systems, thinking about Cartesian versus spherical coordinates or other kinds of coordinates in 3 dimensions. We teach you guys to be careful with units and coordinate systems so that the results that you get at the end of some calculation don't depend on any arbitrary choices. And that's crucial because the world doesn't care about you and me. Right? The world doesn't care about what we choose, or it doesn't care about whether there's some international treaty to use SI units or something like that. And so that is a kind of precision to make sure that arbitrary choices might be parts of the intermediate steps we use to do a calculation, but they don't determine what's the final result of any calculation. And that's guidance for how we think about problems in the rest of life as well. So that's for physics in general, as applied to other subjects. For quantum mechanics in particular, it has a real reputation in the general culture. And there are people out there who might believe that quantum mechanics is a fuzzy subject because it sounds sort of fuzzy to think we have uncertainties in things, or to think that we don't know whether a cat is dead or alive, that sort of thing. And so it gets that reputation, but what I've tried to show you over the course of this semester is that quantum mechanics is a very precise subject, right? That we work hard to do precise calculations. Quantum mechanics is a precise subject which makes precise predictions about fuzzy things, right? That there are properties of electrons or other quantum mechanical particles which are fuzzy, but we say precise things about them, and we can precisely characterize what we do and do not know. And so this idea of making precise predictions about fuzzy things is something which I hope you'll be able to carry into anything else that you might want to do in life. All right, so that wraps up what I wanted to tell you for this class, for this kind of a summary. I'm happy to stick around and answer any questions that you might have. If you don't have any, then I will wish you well and say goodbye here. And so good luck on the final, and good luck with whatever you go on to do past this semester. So long, everybody.